The second model from Key et al. 2014 uses a weighted linear combination as a decision rule for determining the decision set for suitability for kudzu. Weighted linear combinations are the most popular and most used type of decision rules in multi-criteria evaluation with spatial data. One issue with using a Boolean and as well as thresholds in the first example is the fact that does kudzu really care if the precipitation, for example, is 1499 millimeters per year? Will it not grow at 1499 and only at 1500 or greater millimeters per year? Does it really care about whether or not it's 146 frost-free days? What about 145 or 144? Well, we know that plants and stuff don't have these hard boundaries. And when you have just hard boundaries and just two of them as factors, you end up with that idea is implicit that, well, at this critical threshold, you either have or have not the ability for kudzu to survive. Now that can be true for some species, for example, like we saw with durian. When we look at durian, we found that durian can't survive when it's 7 degrees or colder. So that's its critical temperature for death. But above 7 degrees, well, some temperatures will be much better, some temperatures will be worse. If it gets too hot, for example. But generally, it doesn't care too much about the temperature as long as it's in the tropical range, so about 20, 24, 25 degrees Celsius every day. That's the best thing to do, right? But at 27, it's still good. At 21, it's still good. Just maybe not optimal. And one way to get around that idea is to give different weightings or ranks to different values of the environmental variable. In the table 3 here from Key et al., what we see for the factors, again, are the same ones we had in the Boolean decision rule. Here we have number of frost-free days. And then we say 0 to 145 days is 1. So we're admitting then that between 0 and 145 days, there's still a possibility of kudzu growth. Now it's very unlikely to be 0, and it's but more accurately near 145 days, like 138, 135, maybe 142. It's still possible kudzu could survive, but it's the least likely. So we give it a 1. Between 146 and 200 frost-free days, well, that's no problem. We give it a 2. Kudzu would be fine in that situation, although the best would be 200 to 365, so we give it a 3 to that value. So 3 in this case is more than 2, and 2 is more than 1. We don't know how much more, but relatively speaking, we give a rank of 1 to 3 for different temperatures. And that helps slightly compared to just giving 0 to 145 1 and everything else 0, like we did with the conditional decision rule using the Boolean and previously. Likewise, we have to say, okay, 0 to 145 days, we rank it as 1. What's the equivalent from kudzu's perspective for mean annual precipitation here? Well, we say 1 to 1500 millimeters per year is a 1. So that means that 1 has the same influence on kudzu as 0 to 145 days. And that's what I'm talking about when I talk about equivalence of these ranks, that 1 must mean 1 for all the input factors. So you have to figure out from the perspective of kudzu what a 1 is in all the different factors. Here we just have 2 to deal with. And the authors have, based on their knowledge, have decided to use 1 for both of these. And then 2, 1500 to 3000 millimeters is a 2 here. And that's equivalent to a 2 here, 146 to 200 days. How they came about that logic has to be justified in some way. And then, of course, for 3, we had, remember, 201 to 365 days. And mean annual precipitation, 3 to 4,500 millimeters is a 3 here. 3,000, I mean, to 4,500 millimeters is a 3. And that's equivalent to a 3 here. So these rating levels, or rescaling values, or rescaled values, must be equivalent across factors in terms of their meaning to the establishment of kudzu. Then, at a second level, we have different weights for each layer. So we say that we give 60% importance, or a weight of 0.6, to the number of frost-free days. So that's slightly more important overall than mean annual precipitation, which has a 40% influence, or 0.4 factor weighting. So that's not equal weighting as you see here. This is giving different weights, but the sum of the weights equals 1, and that's the important thing. Well, it's one of the important things. It has to be equal to 1 or it doesn't work out. And by doing so, the output values for the decision set, each cell will have a range between 1 and 3. If we didn't use this, and we just added them together, for example, well, we'd have a range between possibly 2 to 6. But with this weighting, our range will be within or less than or equal to 3 and greater than or equal to 1. To understand weighted linear combinations, we have this following equation here, S, where X is a raster layer, one of the factors. So X equals a factor that goes into the decision rule, where the decision rule here is a summation. So it's the raster layer times its weight divided by the sum of the weights. And where the sum of the weights equals 1, we just have this. And that's what we're doing. So because the sum of our weights sum to 1, we simply take the sum of the raster layer times the weight plus the next raster layer times its weight plus the next raster layer times its weight. And that's what we mean by weighted linear combination. And that's why it's important for the sum of the weights to equal 1, like so. And then we have two special cases where each weight is 1 over n, where n is the number of raster factors or layers going into the weighted linear combination. If we have 2, for example, in our case we have the precipitation factor and the temperature factor. So n equals 2. So 1 over 2 is equal to 0.5 when n equals 2. In that case, we have what are called equal weights. Even if you have 7 layers, 1 over 7 is the weight for each layer. And that ensures that the minimum and maximum values that can come out of the weighted linear combination are equal to the minimum and maximum values of the rescaling system that you used, in our case 1 to 3. The next special case is when we have just the sum of the factors without weights. And that's called a direct linear combination rather than weighted, because there are no weights to take into account here. The output of this, the output of that and equal weights look exactly the same, except for the fact that the scales or legend values will be different. And that's the only difference between a equal weighted linear combination and a direct linear combination. So as a cartographic model, we have the following two input or factors: days greater than 0 degrees Celsius and precipitation in millimeters. Let's start with precipitation. To rescale it, we use what's called the reclassify tool in the toolbox. So this tuple here of three things, right? The basic component of a model is a process, so that's a single process. Precipitation is reclassified into 1, 2, and 3, according to the table that we saw. Then we multiply it by its weight. In our case, in this example here, we're using equal weights. So we use 0.5 because 1 over n, where n equals 2, is 0.5. So in the second component here, the second process, we multiply the factor times its weight to get a weighted factor. For days greater than 0 degrees Celsius, we do the same thing. We reclassify into the scale of 1 to 3. Following that, we multiply the output of the rescaled days greater than 0 degrees Celsius by the weight 0.5. Again, these are equal weights, 1 over n. And that gives us this intermediate value, these two intermediate rasters right here, which are the products of each input factor times the weight. Then to sum them, we use the plus right here. This intermediate factor plus that intermediate factor equals the weighted linear combination, or prediction of Kudzu, based on the rescaling of temperature and precipitation in a ranking of 1 to 3. And just arithmetically, it's shown down here. So as a weighted linear combination, we have, again, each raster times the weight. So we have our reclassified raster times 0.5 plus reclassified raster times 0.5. And we don't use any, I'm not using parentheses in the top here, although I need to in reality, because we have this over that. I don't need to in this visual example because it's a quotient here. Plus has a less precedence than multiplication. So automatically, this happens first, that happens second, and then the plus happens third. And then that is divided by the sum of the weights, which is 1, which equals 1 here for this weighted linear combination. In terms of doing it with map algebra in Python, we have to do or create first what we call a remap range variable. So that's just like a neighborhood variable that we created previously in the other module 4. So a remap range in this case looks like this. It has parentheses, just like any function. So it's an opening and closing parentheses. Then within that parentheses, it has what's called a list of lists. An open list bracket, let me just get that better here, an open list bracket right there. My pen isn't writing now. Right there. And then the closing bracket right here. So that defines what's called a list in Python. Then within that list, we have sublists. So for example here, the first sublist has again an open bracket and a closed bracket. And in that first sublist, we have what's called a remapping range. So we're saying from 0 to 145, make that 1, comma, for the second rank, again, open bracket and closed bracket. And then in the brackets, we say 145 to 200, any values between 145 and 200, make it a 2. And in the third one here, we have 200 to 365 growing degree days, make that a 3. And you might be wondering when you're looking at this, how come this number overlaps with this number and this number overlaps with that number? They're both the same numbers. You might think, well, that's going to cause confusion because how does it know how to deal with 145? Because this is inclusive here. 0 to 145 is inclusive. That means any value 0 to 1 equal to 145, including 145, is included in 1. Now, automatically, because it has an implicit notation, implicit set understanding here, it knows that this 145 means slightly over 145. So 145 point trillion zeros to 1 to 200 inclusively. And so I'm just showing you the set notation down here so that makes it clear. So square brackets mean inclusive. So A, comma B, inclusive. And then we have a parenthesis, B, comma C, inclusive. And then again, parentheses D, so it means just over D, to E, inclusively. So you understand that the remap range variable knows how to treat those values. And so we have to make sure that we include them. We don't put 0 to 145 and then put 146 over here, because then it would miss anything slightly greater than 145 to 146. We don't want that to happen. So it knows about set notation, even though it doesn't use it explicitly, and that's just because of the data structure called a list variable in Python. So we create that remap range. There's also remap value as well. So we say temp remap, and then we say reclassify. We put in the days greater than 0 degrees Celsius. We want to do the values, that's the value of each cell, according to this thing here that we created, the remap range variable. The output then is going from the temperature. I'll just call it temperature. It's really number of days greater than 0 degrees Celsius, but temperature is the overarching variable here. And then outputs this. So we have 3, 2, and then 1s over here. So with regard to the establishment, propagation, or reproduction of kudzu, this is the variable for the number of frost-free days. So according to the number of frost-free days, anywhere in the green is best, second best, and third best. And then we have to do the same thing for the precipitation. So precipitation, we use a remap range, again, open list, close list, and then we fill in with lists separated by commas. So 0 to 1500 millimeters, recode that as 1. Anything greater than 1500 to 3000, encode it as 2. Anything greater than 3000 to 4500, encode it as a 3. So we go from then precipitation to here, where all the green area is 3, or I should say, no, not the same colors as the previous one. My mistake here. 1 is green, 2 is purple, and 3, the highest amount, you can't see it on here because it's just a small little places, a few small places in Florida, or actually not in Florida, but over here on the West Coast, which have more than somewhere between 3 meters and 4.5 meters of rainfall a year, or precipitation, not necessarily rain, right? It could be snow as well. But I should have used the same colors as on the previous one, which I didn't. It's my fault, but you understand the idea here. So now we have these two variables. So now we have our precipitation and our temperature. So these are the two factors, and we're going to equally weight each factor. So temperature times its weight of 0.5, precipitation times its weight of 0.5, and then we add them together. And here I'm just using parentheses to make things very explicit. although I don't need them in this statement because the order of operations states that plus comes after multiplication and division. Now the result is then right here, and you'll see it has a range of 1, 2, 3. So the same range as the input, any one of the input factors, where 1 is the least suitable, these areas here, and 3 is the most suitable. And so we now have a suitability scale instead of just a yes or no like we did with the conditional decision rule. So our candidate set, I should say our decision set here, ranges between 1 and 3, and we have a gradation of values between there. 1's being the least likely, 3's being the most likely, and then there's the range in between. So 2.5, for example, is also fairly highly likely. So that's, and then there's a 2, which is medium likely. In here are 2, yeah, 2, and then a 1.5 up there, and then a 1's in here. And so that's called a weighted linear combination. The alternative way of doing what we just did using straight up map algebra is to use the weighted overlay function in Python. Now, the weighted overlay function requires two things. It requires a set of remap values and a weighted overlay table being created. The remap values, if we just says what goes to what. And in our case, we have, again, something that goes from 1 to 3 here and 1 to 3 here. So we just want to maintain that 1 to 3 and 1 to 3. So we have a remap vals right here, and that's just a remap value instead of remap, the other remap that we did, remap range. And we just want 1 going to 1, 2 to 2, and 3 to 3. So in other words, don't change. We're just saying don't change these because they're already weighted 1 to 3. But what you could do is if you hadn't weighted them 1 to 3, you could create 2 remap ranges or 2 remap values and use them inside the weighted overlay table instead of having just 1 to cover both of them. So if you didn't previously rescale them, you can rescale them during the creation of the weighted overlay table by inserting the remap objects here and here. Now, in the weighted overlay table, again, it has a number of different things in it. First is a list of lists, and then 131. The 131 as the second input here is a from to by. So it just means we want the output to range from 1 to 3 by 1. That's all. And you could change that if you wanted to have it from 1 to 6 by 1 or something. But we generally don't. We just keep it the same as the input scale. Now, in the WO table, we start with that list of lists, and each component in that list is a list itself, where we give the variable, for example, here's precipitation, its weight as a percent rather than a proportion, what we want to use, the values of each of the individual cells, and then the remap values right here. And again, it's here that you could put the original remap objects that we created to create the rescaled values if you wanted to do it all at once. And then likewise for this, the output, temprec. Once we have the weighted overlay table, then we just put that into the weighted overlay function. It just takes that one thing. And it then spits out this, which has 1, 2, and 3. 3 being the best, and 1 being the least. Least. Let's draw that better. Anyway, you know where the least is. It's this color in here. Now, you'll notice here that there's nothing in between 1 and 2 or 2 and 3. And that's because the weighted overlay table, or the weighted overlay function, only outputs integers. So it cannot output decimal place or non-integer layers. Why? You might ask, does it do it that way, whereas in the previous map algebra statement we were able to get between 1 and 2 and like 1.5 and 2.5 and 3. It comes down to the theoretical idea that we don't know how much different a 1 is from a 2 and a 2 is from a 3, because these are ordinally ranked values. So we don't know that 1, is 1 unit away from 2, or 2 is 1 unit away from 3. Technically it is algebraically, but in an ordinal ranking, we don't know what that ranking took into place. So we don't treat it as a continuous variable. And so we want to only be able to output integers. Now, we did it the other way by saying, okay, well, here's the straight up addition of the layers times their weights. And then we get a continuous variable coming out the other end, which has decimal places. And if we find something as 2.5 on that one, for example, we know that that's slightly better than 2 and not as good as 3. And that's okay as well. That's the usual way of doing it. But just keep in mind that we don't know how much. And so 2.5 doesn't necessarily mean it's 0.5 units away from 3 and 0.5 units away from 2. Because our units are just relative scale things here. They're ordinally ranked. And so we can't say anything solid about that. We just know that certainly it's slightly better than 2 and less good than 3. But we can't really say it's half between them as such. And so we have to keep that in mind. And that's why the weighted overlay function doesn't do that. Now, in terms of sensitivities for the weighted linear combinations, we have sensitivities around the value ranges and the weights. So these are the value ranges that we chose for temperature and precipitation. And if any of these thresholds change, so will the output. We also have different weights. So here, 0.4 and 0.6. We use 0.5 and 0.5. If we change it to 0.4 and 0.6, it's very easy to do. We'll see how to do that in the worked example next. But changing those weights will change the output somewhat in terms of where we find 1s and where we find 2s and where we find 3s in the decision set. So we have to keep in mind those sensitivities. And there's also implicit sensitivities here, in that we might just change 1 to better correspond to 1 here. Remember, these are equivalencies. 1 here equals 1 there. But 1 is not 1 unit away from 2. It's just ordinally ranked as 1, 2, and 3. We could use ordinal rankings of 1, 50, and 75. Because they're almost like labels. But not quite. They are ranked. So, but there's inequality, but that's all we know is that there's inequality. We don't know how much that inequality is. So there is that also implicit idea that, well, did we get our equivalencies right with respect to Kudzu establishment, propagation, etc.? For the second model of Key et al., we're going to be undertaking a weighted linear overlay. And so we're also going to need in here, according to the different factors present, we need the number of frost-free days again and mean annual precipitation. And we have these particular cutoff points, 0 to 145, 146 to 200 days, and 201 to 365 days, coded into a scale of 1, 2, and 3. And likewise for mean annual precipitation with these critical ranges. From now on, I'm also just going to do the Python examples because it's more efficient and it's better for you to learn that than model building. If you want to make the model, the reference, of course, is within the module example PowerPoint video. So here, I'm going to start by going to my analysis and set my environments, my global environments. output coordinate system to match precip, extent to match precip, cell size same as precip, cell projection method preserve resolution, mask precip, and snap raster precip. And I'll click OK. I'm resetting these because I brought these into a new session of ArcGIS Pro that I'm starting with. Then I'll open the Python window. So since it's my first session of Python in this session of ArcGIS Pro, I'm going to say import. I'll say from arcpy.sa import all. And then from arcpy import env. I'm just going to check an env setting like snap raster to make sure it's been brought in. And hopefully they've all been brought in and we don't get any errors. We'll find out. So in order to reclassify, we'll go with the days greater than 0 degrees Celsius first, and I'll make a raster variable out of that. And I'll just call it t temp equals raster, and we'll choose the days greater than 0 degrees Celsius. Then I need to be able to reclassify that according to the critical values we see here, 0 to 145, 146 to 200, 201 to 365 as 1, 2, and 3. So we're going to have to use a remap range object. So I'll say rmap equals remap range. And remember, this is now going to be in a list of lists. So I'm going to start my lists with that. That's the main list. And I can make some space in there if I want. And then inside here, I'll have 3 other lists, each for one of the new levels that we are recoding or standardizing the days greater than 0 degrees Celsius to. So I'll put open close bracket, comma, open close bracket, comma, open close bracket. So I make that form, the syntactical form that's necessary first. Now I say from to, and what's the new value? So 0, comma, 145, or 140, yeah, 146 is going to be a 1. So that corresponds to 0 to 145 days is 1 here. Maybe I should put that as, yeah. And then over 140, that should be a 145, sorry. 0 to 145 is 1. And then 145, comma, 200 will be, comma, 2. Then I'll just make this, I'll try and catch the edge of this window here so I can make it bigger so we can see it all in one statement. Okay, so the last one is going to be 200, or is it 201? No, it's a 200 days, and then anything over 200 days to 365 will be 3, the most suitable for Kudzu, established from propagation, etc. So I now have that remap range variable. So it's an object and it's just held right there in RMap. If I want to see what's in RMap, I can just say RMap and it shows me. So now that I have that, I can reclassify, and that will produce my factor for temperature. So I will say T temp F for factor equals reclassify, and then what I want to reclassify will be the temp raster, TEMP, and then I want the reclass field value, and finally the remap object is RMap, like so. And I can have a look at my result, and we can see that we have 1, 2, and 3. 3 is purple in this case, red is 2, and 1 is blue. So 1 is the least suitable, red is the slightly more suitable, and the most suitable of all here is purple for the temperature conditions. The next variable we'll deal with is the precip. So I need to do the same thing. I need a remap range for that. So I'm just going to reuse, I don't need my old remap range anymore, but no, let's keep that RMap one, and we'll call this for the second remap range PMAP. That'll be equal to, again, range. So, and then in the parentheses, set of brackets, and then in those brackets, 3 sets of brackets, 1, 2, 3. And then the first one will have the from and to as the first standardized value. And we just go back to our page here, and we can see that's 1 to 1500 millimeters is 1. So we say 1 to 1500 as 1, and then 1500 to 3000 as 2, and then 3000 to 4500 as 3. And that creates our remap range for the precipitation. Next, I can create the factor. I'll call it precip F equals reclassify. And in here, we'll be reclassifying temp, the value field again, and then the remap object is pmap for this one. Oh, I think I had a syntax error for some reason. Ah, yes. So up here, I had a syntax error in my remap range in that I accidentally deleted my closing outer list bracket. So I'll just put that in there and go down here. Oops. Put that in there and hit enter. I reclassified the wrong one as well. It shouldn't have been temp. It should have been precip. Did we make a raster variable yet for that one? No, we didn't. So that's why. Okay. First, we'll make the raster variable precip equals raster, and that will be the precip millimeters. The output here is just 1 and 3, but this doesn't make sense. Notice as well, I made a mistake up here. So I'm looking at my output again. Before it was 1, now it's 1 and 3. And it doesn't quite make sense, does it? Because I should have 1, 2, and 3 coming out. So that means I must have made a mistake elsewhere again. So here I look at, oh, pmap, there it is. I accidentally put a 3 here. So I'll just go back up there, fix that 3, make it into a 2, and hit enter again. There, now we have 1, 2, and 3 for precip. We know what 1 should look like. Our 3s, well, they're hard to see just because there's not a lot of 3s here. But if we zoom in, let's say to the west coast, there's a little pocket of 3s. So that's over 3000 millimeters per year precipitation. And the 1s are all the pink area, and the 2s are the green. And you can always validate that in alternative ways too, right? So you can check. I can say, okay, I'm going to turn off all my layers except for the precip factor and the precipitation. And I'll click anywhere to see what the values are of each of those layers. So 1 is 217. And we know anything from 0 to 1500 millimeters is going to be a 1. If I click somewhere in a green area, that should be over 1500, but less than 3000, or just up to 3000. And that's 1616, so we know that's good. Right there, 1616 for 2. And then our little pocket of 3s over here, that should be over 3000. And that's 3187 millimeters. So that's another way to do an ad hoc validation to make sure that what you're getting is right. And that's the purpose of all these errors here, is the idea that, well, you must check what comes out to see what happened. Because remember, when I did these, first everything is a 1 or a 3. I didn't get errors when I did that, right? So there were no errors coming up when I had that mistake in there. This one I had to fix. Likewise, we had 1 and 3 only. So we didn't get an error when we had 1 and 3. It just spit it out. And you might think, well, because it spits out a result, there's nothing wrong with it. That's not a logical conclusion, because you being right and the computer spitting out something without a error message is not equivalent to you being true, to what you've created, I should say, being correct. So you have to be responsible for what's correct, and you have to check the output and say, okay, does the output make sense? So syntax errors are very common, and that just means you've misspelled, let's say, what you're supposed to have as the form of the statement that you put in. And in this case, we have to have inside the remap range a list of lists. And it even pointed to where the syntax error occurred, which is right here. And so that means that, well, I could look at here, do I have the right form? I know I need a list of lists here. And I don't have that, so I add an extra one in, and then I don't get a syntax error. Now, we can go and combine the precip factor and the temp factor. For equal weighting, we give a weight of 1/2 to each one. So I could say suitability, I'll just call it suitable, equals the temp f, times 0.5 plus the precip factor times 0.5. And then we have our suitability. It looks like that. And its range is somewhat weird because it's going to 183.5, and I don't think that's correct. So I'm just going to try the appearance symbology. Why is there a 183.5 in there? So that means something must have been missed elsewhere. So we should only have the scale going from 1 to 3, and for some reason we have from 1 to 183.5, and that means something went wrong along the way. So what could be the 183.5? So the value of temp f down here, what's 1/2 of 365? Approximately, it's 182.5. We get about 183.5 popping out here. And if we look at the temperature factor, look at, we got 1, 2, and 3, and then suddenly 365. 365 is not one of the scales, is it? So in the temperature, we have 1, 2, and 3. Now, we only find this at the end by validating or ad hoc validating what we have coming out. And we know we should have something between 1 and 3 coming out. In the temperature factor, we used an interpolation method that can provide values slightly outside the range of the input values. The highest value was 365.468. Whereas when we did our remap object, our biggest number was 365 right here. Whereas we need to have something larger than 365, like 366, for that to work. So I just go back and I fix that. And then I go back to the temperature factor and I redo it. And now we see temp f has 1, 2, and 3. So I'll remove that old temp f there. So now we have precip f with 1, 2, and 3, and temp f with 1, 2, and 3. So now we can run our last suitable statement again, and things coming out of here should be between 1 and 3, and they are. So I'm going to go back to my symbology on the appearance tab, classify, there we go. Primary symbology to be unique values. And then we have our 1, 1.5, 2, 2.5, and 3. And then we just have to use a continuous scale, like this, for example, or maybe we want to invert it. So I'll go down, format color scheme, and I'll flip it, click OK. So from the colors, we can see that 1s are the lightest color blue. If you're the least suitable, then you have 1.5s, all the way to 3, which is the darkest. And if we compare this, let's say, with the current distribution of Prairie, Montana, or Kudzu, and I'll go back to catalog, and I'm just going to bring in the actual Prairie, Montana, just to have a look at where it is compared to this model. And so this model, because it has gradations of suitability, we see that most of the existing Prairie, Montana is certainly within the zone 2. Not zone, but level 2, the suitability value of 2. And outside of that, there's none. But there's also a lot of space within that second region, space where Prairie, Montana might also be suitable according to these factors. So that you could say that this particular model matches better than the first model did, which was the Boolean one, which had no correspondence at all with the current reality of where Kudzu was observed.